I am happy to deliver the inaugural lecture in this series, The Expanding Mind, and I have chosen for my subject the origin of life. I would like to discuss today the origin of life on our planet in a slightly wider context and perspective than is usually thought to be necessary. First of all, I think we must concede that there is a logical need to understand an origin of life, at least as far as the Earth is concerned. The Earth today is surely teeming with life, and organic molecules exist in great abundance. But this clearly was not always so. 4.5 billion years ago, the material of the Earth was in the form of a cloud of fine dust particles that were getting together, condensing and contracting to become the primitive Earth. And for a while afterwards, when the Earth had itself condensed into a solid body, its molten crust would have been too hot for any organic molecules to persist. There are good reasons to believe that much smaller condensed bodies in the form of icy comets from the outer regions of the solar system subsequently impacted on this cooling planet and deposited volatile materials, including water, that went to form the Earth's oceans. Evaporation of water from the oceans and the breakup of water molecules by sunlight then gave rise to an atmosphere and a cloud cover around our planet. Only after this happened could the Earth have become a suitable home for life, with its surface screened and well protected from the damaging ultraviolet radiation from the sun. Let me next touch briefly on a question central to the theme of my talk today. Could life have emerged from non-living matter here on the Earth? The production of organic molecules of rather great complexity, for example sugars, nucleotides, amino acids, are a necessary condition for the origin of life. But the production of these substances alone are by no means enough for the origin of life. The vast majority of organic molecules we find today here on the Earth are either directly or indirectly the product of biology. There are, of course, abiotic or non-biological conditions that could lead to the production of organic molecules from inorganic ones, and there have been several classic experiments to demonstrate this. Perhaps the most famous of all is the Urey-Miller experiment, which was carried out nearly 30 years ago. In this experiment, a flask filled with hydrogen, water, methane and ammonia in appropriate proportions was sparked with an electric discharge, and it was found that traces of biochemical substances were formed. This result, showing as it did that the basic chemical building blocks of life could be produced non-biologically, appeared at the time so dramatic that it had a profound psychological impact on the world of science. Many biologists were led to believe quite firmly that they had come near to understanding an origin of life in terms of processes that may have taken place here on a primitive Earth. Yet a few odd amino acids and sugars produced under contrived laboratory conditions comes nowhere near the exceedingly intricate complexity of life itself. And it is a far cry from proving that life could ever have started here on the Earth. On the contrary, a terrestrial origin of life would, for many reasons, seem most unlikely. The conditions on a primitive Earth are most unlikely to have been appropriate even for the production of the building blocks of life, let alone for the origin of life. And even if the chemical building blocks of life were supplied, God-given say, in some terrestrial pond, their assembly into life would well nigh be impossible. The Earth is too small, the available timescales too short, and life is far too complex for this to have ever happened. Many biologists who think that an origin of life took place here on the Earth implicitly favor a miracle. The argument goes as follows. Given all the right starting materials, the origin of life is such an improbable process, occurring with such an extremely low probability, that it could perhaps have happened only once in the entire universe. And the argument goes on, since we know life is present here, it must have started here. This second step does not follow logically, particularly if we admit the possibility of transferring microorganisms such as bacteria from one part of the galaxy to another distant part. The Earth-centered view of life that biologists hold is essentially pre-Copernican, and its adherence leads to many serious difficulties in understanding and interpreting biological data. Let me now turn to evidence. The first sedimentary rocks on the Earth were laid down through the effects of rainfall and water erosion of an initial crust at about 3.8 billion years ago. Until very recently, a few months ago in fact, it was thought that there was about a 500 million year time span between the laying down of the first sedimentary rocks on the Earth and the start of life. And the origin of life, up to quite recently, was thought to be recorded in the form of microfossils of bacteria and algae in the Swaziland cherts, rocks in a certain mountain formation in South Africa, which were dated at about 3.4 billion years ago. If this were true, there might have been about a 500 million year time span for some kind of primordial soup to have developed and brewed on the Earth, at any rate according to the conventional theory. This seemingly comfortable situation for the conventional theory has now been dramatically shattered. Geochemists have recently discovered that there are the most unambiguous signs of life in rocks from the Isua region of West Greenland that have been dated at about 3.83 billion years. These rocks represent perhaps the very first record of sedimentary processes here on our planet. The primordial soups seems to have just about been squeezed out of existence from the geological record. There is now evidence that the Earth was showered with living cells from the very dawn of its creation. Life got a toehold on the Earth at the very first moment that physical conditions became favorable. A hitherto sterile Earth might be said to have become infected with life, a life which thereafter began to evolve against the background of continually changing local conditions on the Earth. If life did not start here, we might ask the question, where did it first start? The number of possible sites for where life could have first started are of course legion. In our own solar system, we can argue that the conditions in the interiors of any one of 1,000 billion comets are better suited to this event than conditions that could ever have existed on the Earth itself. And with more than 100 million sun-like stars in the galaxy, the probability of life first starting on any comet in the solar system would be so minuscule as to be totally negligible. Life could have first started with equal probability on any one of 10 billion comets in the galaxy. So, to assert that this event occurred on an object within our own solar system must be regarded as most arrogantly egocentric. Bacteria have sizes that makes it difficult for them to remain confined in orbit around any star. Starlight has the property of being able to expel particles of bacterial sizes away from the gravitational attraction of a parent star. Bacterial cells are thus explosively propagated throughout the galaxy, no matter where their first origin occurred. Bacteria on the Earth have properties that are difficult to reconcile with the usual concept of a terrestrial origin and evolution of bacteria. The total mass of bacteria on the Earth, mainly in the soil and the seabed, is about 10 billion tons. The number of bacterial species involved here is probably vast. One of the most striking features about the distribution of terrestrial bacteria is that they are never optimally matched to the environments in which they are found. If bacteria are indigenous to the Earth, one would expect an almost precise adaptation of organisms to niches, and this is not found. For example, the distribution of two classes of bacteria, the heat-loving bacteria and the cold-loving bacteria, presents a continuing puzzle. A large fraction of bacteria in tropical soils are of the cold-loving type, bacteria that could only multiply at temperatures below freezing, temperatures that are never realized in the tropics. Conversely, a large fraction of the bacteria in the Arctic and Antarctic ice shelves are of the heat-loving sort. These properties are readily understood if the Earth is bombarded with an astronomically vast range of different bacterial types. The various niches on the Earth pick up and amplify the types best suited for replication under the conditions that locally prevail. There are other properties of bacteria that can be regarded as being distinctly unearthly. For instance, bacteria have the property of being able to survive almost indefinite periods of time under the low temperature conditions that exist in interstellar space. Bacteria can withstand and survive doses of ultraviolet radiation that are never received on the Earth. Some bacterial types have an uncannily high resistance to X-rays, gamma rays, and even cosmic rays. All these properties are readily explained if bacteria evolved on a galaxy-wide scale and were inevitably adapted to be space travelers. These space-traveling microbes, dispersed throughout the galaxy, would be part of the legacy or initial biological endowment of any cloud of gas in space that is condensing into new stars, comets, and planets. Those bacterial cells which find themselves in suitable environments within comets then multiply in vast numbers and are showered back into space. A large fraction of all the carbon in the galaxy could thus be tied up in the form of microbial cells. Astronomical evidence provides overwhelming support for this point of view. The most crucial astronomical clues have come from a study of interstellar clouds, clouds of obscuring material that are known to exist in the space between stars. Interstellar clouds show up as conspicuous dark patches and striations against the background of stars along the Milky Way. Several generations of astronomers have pondered on the composition of material within such clouds. Recent observations, including measurements using Earth satellites, together with modern techniques of radio astronomy and infrared astronomy, have provided a wealth of new data. A large fraction of the mass of the entire galaxy is in the form of gaseous molecular hydrogen within these clouds. It has recently been found that large quantities of organic molecules are also present. In all, about 24 or so gaseous organic molecules have been discovered. But perhaps the most baffling component by far is a population of tiny microscopic dust particles that inhabit the clouds, particles that cause the blacking out of the light from distant stars. For nearly 20 years, Sir Fred Hoyle and I have strived to find a particle that has the correct properties to match the behavior of these so-called grains in space. But we had little or no success. Then, about 6 months ago, we had the rather outlandish idea to try a comparison of these grains in space with bacteria. To our great surprise, we found that terrestrial bacteria are uncannily similar to cosmic dust with regard to all their known properties. The measure of agreement was indeed so perfect that we were led to conclude that the hitherto unidentified component of interstellar dust clouds were in fact bacterial cells. The total mass of bacterial cells, along with their associated viruses, throughout the galaxy turns out to be truly enormous, measuring some 10 million times the mass of the Sun. The picture which has emerged then is that space is filled with living cells, cells which are mainly in a frozen, dormant state. Every niche suitable for life that develops through collapse of cosmic gas clouds and the formation of stars, comets and planets becomes very quickly infected with this all-pervasive living system. It now becomes almost meaningless to pose the question, where did life begin? Life, on this point of view, must be considered as the sum total of an evolutionary experience gained and accumulated not in one place, but in a multitude of different places, quite widely separated throughout the entire history of the universe. Let us now come nearer home to the solar system and our own planet, the Earth. In our own solar system, we argue that life in the form of bacterial cells and viruses were first housed in the comets. There are about 1,000 billion comets around the Sun, and these are believed to be among the first objects to have condensed in our family of planets. In every one of these comets, there is a warm, watery interior and all the organic nutrients necessary to make for a congenial breeding ground for microbes. I mentioned earlier that comets crashing onto the Earth brought the Earth's oceans and the atmosphere. With the oceans and the atmosphere so deposited, comets would also have seeded our planet with life, a life which under the protected canopy of cloud-covered skies was able to take root and to flourish. The first successful seeding of the Earth with life occurred at about 3.8 billion years ago. But on our point of view, this process of seeding could not have stopped at this distant prehistoric time. Comets are with us in the solar system today, and the Earth continually picks up debris from comets. About 100 metric tons of cometary debris enter the Earth's atmosphere every day. Much of this debris is either sterile due to being in orbit around the Sun for too long, or it is burnt up upon entering the Earth's atmosphere. But we could argue, quite convincingly I believe, that a small fraction of the incoming dust, freshly evaporated from comets, must contain active or viable microbes that actually survive entry through the Earth's atmosphere. This conclusion, bold though it may be, has the advantage of being susceptible to proof or disproof, especially if the Earth is being showered with bacteria and viruses that could cause disease in plants and animals. Creatures on the Earth, animals and plants too, could be regarded as amplifying detectors for pathogens from space. Disease would then effectively be a record of the incidence of space pathogens. A reading of medical history gives ample encouragement for this point of view. Many bacterial and viral diseases have a record of abrupt entrances, exits and re-entrances onto our planet, exactly as though the Earth was being seeded at periodic intervals. In the case of smallpox, the time interval between successive entrances could have been about 700 to 800 years. Historical data point to smallpox being an intermittent phenomenon, with successive disease epochs separated by several hundreds of years that are disease-free. For a pathogen such as smallpox, whose only host is man, global remissions of this disease, lasting for many hundreds of years, are very hard, almost impossible to understand. On the conventional point of view, one has to say that the virus became extinct and then re-evolved to precisely its original form from some unknown ancestor after many hundreds of years. A most improbable event that would be. Historical data is, however, often incomplete, and one may have serious doubts about the genuine absence of any disease from the earth at any given time. But for smallpox, we know that the disease was present a few hundred years before the classical period in Greece, and again, most decisively, that it was present a few hundred years after the dawn of the Christian era. With the accurate medical records that are available at the time, we can equally be sure that smallpox was not present in classical Greece and Rome. A genuine worldwide absence would seem to be implied at this time, for otherwise it would be hard to imagine a disease so infectious as smallpox being kept out for so long from the hub of empire in the Western world. There are many puzzles, too, in the medical annals of more recent times, puzzles that are resolved if we accept that pathogens could be falling from the skies. For instance, there is a group of about 500 trio Amerindians who until quite recently had lived in the dense forests of Suriname, quite completely isolated from the rest of humanity. When the forests were cleared and this tribe was discovered, it was found that there were several polio victims amongst them who seemed to have contracted this disease at times roughly coincident with epidemics in cities hundreds of miles away. There is no conceivable way by which the forest-dwelling Suriname Indians could have contracted polio from those who lived in cities. But of course, the city dwellers and the Indians in the deep forest could have caught the disease together if the disease-causing pathogens rained from above. The attack of pathogens from space is, of course, not confined to man. There is a great deal of evidence relating to attacks on non-human species as well. For example, in the year 1978, a lethal new disease began to take a heavy toll on dogs. The causative virus was unknown before this time. The most remarkable feature here was that the new disease appeared almost simultaneously in widely separated parts of the world. Great Britain, the United States, Canada, South Africa, Holland, and Australia all reported the disease to appear for the first time at the beginning of May 1978. Transmission by contact between dogs can be ruled out, because there is no free traffic of dogs between these countries, and because the most stringent quarantine measures are everywhere quite ruthlessly enforced. So this simultaneity of attack, I think, clearly points to an invasion from space. Perhaps the most impressive evidence of all for diseases coming from space comes from a study of the incidence of influenza, or flu as it is more commonly called. It has been known for many years that epidemics of flu strike fairly vast tracts of a country almost simultaneously and appears to spread far too rapidly for it to be caused by one victim infecting another. For instance, Dr. Robert Thomas, observing the pattern of several epidemics and writing as far back as 1813, has had this to say, I quote, "By some physicians, influenza is supposed to be contagious, by others not so. Indeed, its wide and rapid spread made many suspect some more generally prevailing cause in the atmosphere as alone capable of accounting for its extensive and speedy diffusion." End of quote. The records of later epidemics reveal the same general pattern. Perhaps the most disastrous influenza epidemic in recent times occurred in 1918-1919 and caused some 30 million deaths. After carefully reviewing all the available information about the spread of influenza during this epidemic, Dr. Louis Weinstein has recently had this to say, I quote, "Although person-to-person spread occurred in local areas, the disease appeared on the same day in widely separated parts of the world on the one hand, but on the other took days to weeks to spread relatively short distances. It was detected in Boston and Bombay on the same day, but took 3 weeks before it reached New York City, despite the fact that there was considerable travel between the two cities. It was present for the first time at Joliet in the state of Illinois 4 weeks after it was first detected in Chicago, the distance between those areas being only 38 miles. End of quote. 30 years on, and it was the same story all over again. The worldwide epidemic of 1948 apparently first started in Sardinia. The Sardinian doctor, Professor Magrassi, commenting on this, writes, I quote, "We were able to verify the appearance of influenza in shepherds who were living for a long time alone in solitary open country far from any inhabited center. This occurred almost contemporaneously with the appearance of influenza in the nearest inhabited centers." End of quote. One of the most striking features throughout this whole story is that the technology of human travel has had no effect whatsoever on the way that influenza spreads. If influenza is indeed spread by contact between people, one would expect the advent of air travel to have heralded great changes in the way the disease spread across the world. Yet the spread of influenza in 1918, long before air travel, was no slower, no different from its spread in more recent times. With such an impressive dossier on the spread of influenza at lightning speed, it would seem almost redundant to attempt further proof that this disease did not propagate by person-to-person contact. Yet a controlled experiment was clearly desirable, and this is precisely what Sir Fred Hoyle and I set out to do for the influenza outbreak that occurred in England and Wales during the winter of 1977-78. The type of influenza virus involved in this epidemic was already quite remarkable. It was a type of influenza that was present 20 years earlier and which had essentially been extinct in the intervening years. The reappearance of precisely the same virus after a lapse of 20 years is readily explained on our hypothesis if it was deep frozen in a comet which was circling around the Sun. Young adults under the age of 20 and school children who would not have encountered this virus during their lifetime would of course have been susceptible hosts. So we decided to look carefully at the way the epidemic affected school children in England and Wales. We essentially treated school children in this natural experiment as amplifying detectors of the virus, in the same way that astronomers use electronic detectors to detect cosmic rays. Data from English and Welsh boarding schools, which we carefully studied and analyzed, showed little or no transmission from case to case. This was particularly evident in certain schools where we could trace the positions of dormitories of those who succumbed and those who did not. There were many cases of 2 adjacent boarding houses, with children in one house badly affected, to the extent of, say, something like 30%, and where the other neighboring house was virtually unscathed. Since the children in the 2 houses mixed freely in both playing field and classroom, this result was surprising, if the disease was in fact infectious. There were other instances where flu raged through a whole school, affecting on the average 1 child in 3, but there was one house where only 1 child out of a total of 60 was attacked. In other cases, a whole school was more or less uniformly attacked. But again, the disease could not have been infectious, because the epidemic stopped quite suddenly before all the susceptible children were affected. We had now obtained quite decisive evidence that influenza was not a transmissible disease, and that its incidence at ground level was rather intimately connected with meteorological factors such as storm conditions, rainfall, and wind. According to our point of view, reservoirs of influenza virus are periodically resupplied at the very top of the Earth's atmosphere. But small particles of viral sizes tend to remain in suspension high up in the atmosphere for rather long periods of time unless they are pulled down to the lower levels. In high-latitude countries well outside an equatorial belt, such processes, where the upper and the lower air become mixed, are seasonal and occur during the winter months. So in a typical European country, the influenza season would start, say, around December and end around March. Frontal conditions involving high wind, snow and rain, so prevalent in the winter months, effectively pull down viral pathogens close to ground level. The virus comes down in raindrops that often evaporate close to ground level, and then it is caught in the complex turbulent patterns of the lower air. The flu is allowed to swirl around in the wind and to settle in a capricious way exactly as it is observed to be. So far, so good. All the available data seems to fit quite elegantly to our hypothesis involving an external origin of the influenza virus. But could this hypothesis in any other way be flawed? We know a great deal about viruses, and it might be wondered whether any known fact about viruses goes against our theory. At first sight, there might seem to be one such fact, a fact which concerns the so-called host specificity of viruses. It is known that viruses, including the influenza virus, are specific to a certain well-defined range of host species. For instance, the influenza virus can attack only a limited number of animal species, perhaps a dozen or two in all, including men. According to the conventional point of view, viruses would therefore appear, on the face of it, to be adapted to certain cells. One could ask the question, how could a virus that evolved in an extraterrestrial site have this apparent adaptation to creatures here on the Earth? Or put another way, how could a cometary virus know ahead of its coming here the range of hosts and the nature of host cells with which it could encounter? Our answer to this apparent difficulty leads to further strength to our argument. Whilst it is true that the incoming virus cannot know in advance about the host cells on the Earth, we, the host cells, could know of the virus, since we have had a long and continuing interaction with these same viruses stretching back over millions of years. We could have become adapted to the viruses, not viruses to us. We go further to say that viruses are in our genes. They are essentially our most primitive ancestors. So it could be argued that we should have no difficulty in recognizing and responding to our own ancestors. Certain types of virus are indeed known to alternate between a latent genetic condition and an expressed viral condition, and there is a considerable body of evidence that points to viruses being in fact an essential component of our genes. We can argue that viral invasions from outside provided the main evolutionary driving force in biology, the main source of additional information needed for the evolution of life. Without a steady supply of cometary viruses, life on Earth may not have evolved beyond the stage of a microbe. In its ultimate analysis, disease caused by viruses and bacteria, although decisively bad for the individual, is good for a species, and appears, moreover, to be absolutely necessary for its evolution. The ideas I have described tonight, both singly and taken together, represent radical departures from currently accepted dogmas in science. Scientists, as a rule, are reluctant to accept such change. But, as I have indicated, these changes of dogma are dictated almost inevitably by the facts that have emerged. Throughout our long history as a thinking species, we have always been loath to accept a model or a theory of the world in which we ourselves did not occupy a central and most important place. The view that the Earth was the center of the solar system was held for centuries and was abandoned only with great anguish after Copernicus. Likewise, we now have come to accept the position that the solar system is not the center of the galaxy and that our own galaxy is not the center of the universe. This same Copernican-style revolution must now be applied to life. Life, with its extraordinary subtlety of design and its exceedingly intricate complexity, could only have evolved on a scale that transcends the size of our planet, the size of the solar system, even perhaps the size of the entire galaxy.